So now I welcome Mr. Advait Gupta. Mr. Advait Gupta is a member of the advisory board of the CFD team of FOSSEE. So Mr. Advait is a founder and CEO of Pandav Applications Private Limited. He has done his masters from Stanford University and is an accomplished engineering professional with exclusive experience in advancing CFD across various industries and academic sectors. So he is the leading developer of the world's first all-inclusive computational physics-based software for additive manufacturing called AM Prava by Pandav. This software is particularly adding immense value to the national defense systems now. So Mr. Advait has had the experience as a senior CFD engineer and AI engineer in the US and has played a key role in integrating CFD into research and industry worldwide as the global head of academic programs. So I think, now I'll just hand over to Mr. Advait. Mr. Advait, welcome to this session.
Sure. Thank you, Payalji, a lot for having me again. And before I start, just want to thank everyone for, especially the FOSSEE team, for organizing this annual workshop. Where you train students in open form and other activities. Basically, proliferating open source software uh, in India across all sorts of institutes, and very very happy to see familiar uh, speakers we don't often get to meet, but I think today is a good opportunity to get updated with what everyone else is doing. I see Dr. Chandan Bose, who's of course leading the FOSSEE initiative. Happy to see his listen to his talk and see his work. I see Mr. Ranjit Desai is there. He's doing a great work in the field of water infrastructure. I also see Dr. Manbendra, doing a lot of good work at CSIR, and other people as well. Uh, while we talk about some of the traditional industries where CFD has been used, I will today focus only on the additive manufacturing industry, and I find it quite intriguing. Uh, the complexity that goes behind understanding 3D printing or metal 3D printing processes is quite challenging. And before we talk about additive manufacturing, let's talk about metals. Let's talk about how we have been working with metals from centuries. And one thing we all have realized, we may have doors, windows, a lot of metal based infrastructure in our own houses, and especially coming from the northern parts of India, where there's a huge swing in temperatures all the way from 0 degrees Celsius up to 48, 49 degrees Celsius. Probably people living in this part of the world feel this uh, feel the behavior of metals quite closely, where metals become brittle at low temperatures. They start creaking, they start cracking, and all sorts of defects, and they are very very sensitive to any changes of the temperature. uh, Traditionally, we have been forging metals. Uh, Temperature gradients in such forging processes are quite broad and very. It's a very slow and gradual sort of process. Cooling is often left for the environment, or passive methods. Thermal history is not very aggressive, and the entire material experiences similar sort of heat exposure throughout the manufacturing. Okay. So the effect for all this is slower temperature responsiveness, limited real-time influences on microstructure across small regions. Then comes additive manufacturing, where processes, especially the processes based on laser, such as LPBF, which is laser powder bed fusion, or direct energy deposition, which is DED. These processes are dealing with very high energy lasers, very high energy electron beams, that heat your metals very rapidly or your alloys very rapidly, and the temperature change happens within microseconds at the locations where the laser is shot at. Each new layer sees its own thermal cycling history, uh, coupled with the thermal cycling history of the previous layers, and the melt pool responds instantly. So, what is the effect of this? That the parts that are manufactured using 3D printing process are extremely high temperature responsive due to localized and dynamic energy inputs. Additive manufacturing has been almost a buzzword. Uh, doesn't come close to the buzzword of artificial intelligence, but it has been around for a decade or more now, and there's been a very clear and steady growth market size for this market when we see from 2017 to 2025, and only expected to grow non-linearly in the next 5 years. As is the case with many markets, the North American market alone shares 34% of the additive manufacturing industry. The parts that come out of AM processes are high performing parts made with high performing materials, and they offer very interesting mechanical and chemical properties, sometimes desirable, but at times undesirable as well. There's a high strength to weight ratio. They are weather resistance. Uh, you can even use multiple biocompatible metals. That could be ideal choice for medical sector. So we have a few examples which are 3D printed, such as gear wheels, gear housing, heat exchanger for turbine engines, and such. Now the question is, we understood what metals are, what are the limitations of traditional forging methods. We understood what additive manufacturing is. Now the question is, and as the title of this talk is modeling before manufacturing, why do we need to model any of this at all? I mean, haven't we been doing this metal manufacturing or manufacturing for centuries? So what's new? Well, if you want to do additive manufacturing, then there is a lot of new things that we still don't understand. We do not understand. We cannot fully predict the behavior of a part that comes out of a 3D printer. And when we don't understand things, we often resort to experiments. So let's look at what sort of experiments are uh, are currently done. And this is a detailed list, but it's likely we may have missed a few tests here. So when we talk about aerospace, defense, or research grade additive manufacturing materials, in broadly speaking, there are four types of tests that we are looking at. We are looking at the part quality, we are looking at the mechanical property, we are looking at the microstructure behavior, and the last one is the build test. Within the part quality, there is density measurement. Within mechanical properties, there's tensile, hardness, fatigue, creep, fractography, residual stresses. So many of the students will identify with these tests. And when we start entering the domain of material science, which is microstructure tests, then we are looking at very expensive synchrotron, XRD, XRI tests, optical microscopy, BST, tomography tests, and other things. Now, if why do we want to do all of this? Because if we do the part quality test, we can understand what are the potential defects that we are going to see, or what are the defects that are already there, hidden in front of your part, inside your part. If you look at the mechanical properties, then we are talking about quality, uh, the of the quality of the product in terms of its strength, its service life, what could be the potential causes of failure, is there any distortion of the component possible. And when we look at material science or the microstructure side of things, then we are looking at melt pool dynamics to capture physics, phase and composition, microstructure information, and we can predict a lot of failures. And lastly, the first three set of tests do not qualify the part still unless the final build test or the part validation and benchmarking is done. Okay. Overall, these process parameters could be what is the uh, power of your laser, what is the scan strategy, what is the material that is using, what is the type of 3D printer, chamber conditions. There are probably 100 such variables that can induce defects in your 3D printed part. So process parameters induce defects in AM builds. Trials are very expensive and wastages cost in millions of dollars per year. Materials innovation and printability is a very long and tedious process. Today, if you want to try a new material or slightly change the composition of your existing alloy, it can take you years before you can deploy it into production. Aerospace certified tests are expensive and time consuming as well. Okay. So a little bit more on the material innovation and qualification. So in the previous slide, we looked at what experiments are needed, why they are needed, and how they help us. So one of the benefits of doing experiments is material innovation and qualification. Currently, we are printing, let's say 4, 5, 6, around 10 alloys, which are on the left hand side. There are some new alloys on the right hand side, another 10 which are under exploration. But what if we want to do tests for 500 new alloys? People and companies are making newer and newer products and requiring very specific alloy compositions. Okay, so if you were to go after qualifying each of these materials, you would be doing bunch of these tests, and that can take a lot of time and a lot of money to be spent. I keep talking about that these tests are expensive, but let's look at what I mean by expensive. So traditionally, you could anywhere be spending 6 lakhs to 9 lakh rupees on validating a small part. If you were to simulate that part, if you were to reduce some burden of that experimentation, you could potentially be saving 65 to 70% of your cost. Okay, so for example, over the next 5 years, if you were planning to spend probably 5 crore rupees on material innovation, on process parameter optimization, using your metal 3D printer, then you can potentially reduce up to 3 crores from that budget just by incorporating modeling and simulation in your workflow. This benefit becomes even more acute when you're going after aerospace, biomedical, and defense grade materials. But even for non sensitive application areas, you will still see the benefits. And simulation and modeling, because it's a software based approach, it's a pure virtual computer based approach. The cost of simulation and modeling gets amortized over multiple research projects, over multiple engineering projects. Right? Let's see if this map opens up. Right. So this is basically a tree showing, uh, overall cost for each of the tests. For example, if you were to do synchrotron XRD, it will take 1 lakh to 2 lakh rupees for a test. With simulation, you can reduce it to 20,000 to 50,000, which is 70% or 80% reduction in price. Similarly, if you were to do traditional, like I said, so if you were to, for example, let's look at X-ray test, 40,000 to 70,000 rupees, but with simulation you can get away with 15,000, and so on. I'm not saying you can totally eliminate the cost, but you can definitely minimize the number of experiments that you are doing. Okay. So we have justified that modeling and simulation can be very fruitful for accelerating the pace of making metal 3D printing a very general sort of used by all sort of technique across multiple industries. um, some of the defects, I keep saying, we can minimize defects, we can predict defects, but what are the defects that we care about when we are talking about additive manufacturing industry. So when you look at a 3D printed part, you will see surface roughness. It could be in the form of humps, it could be in the forms of bubbles, keyholes, spattering, liquid breakup, keyhole porosity, vapor depression, vapor plume ejection. And for example, if you're following my pointer, you can see that there are some bubbles which are entrapped inside the metal. It is not desirable. If you look at this particular case, it's a deep keyhole. Right. Like I mentioned, there are a lot of defects. I was talking about this deep depression. So laser is shot from top. This is a metal plate. You can see the depression has gone so deep, the vapor has gotten entrapped inside. Proper J-shaped keyhole formation here. And then, if you start looking at microstructure data, grain morphology, you can see those effects there as well. There could be pores, there could be keyholes again, there could be poor bonding effect between multiple layers, unmelted powder particles or partially melted powder particles. So this is a very, very complex and fine process, and it's very important to understand what is really happening in your process. Um, so when a additive manufacturing process engineer or a researcher sees a part, he doesn't want to see certain things. He doesn't want to see wastage of material, which is quite a lot at times. You don't desire uh, uh, you know poor grain morphology. You want good surface finish, and there are x number of things that you desire in a particular build part. And there is one aspect of 3D printing which can control all these defects, which is the melt pool geometry, melt pool shape, if you want to call it, or melt pool dynamics, wherein optimizing the process parameters, utilizing advanced monitoring techniques, employing machine learning for defect prediction and control, you can really get the desirable melt pool shape, uh, and consequently you can minimize the defects. So to summarize, all this is currently done using experiments. Optimizing your melt pools, optimizing process parameters, material innovation, R&D. So we have established that all this is currently done using experiments. But if you were to really reduce the cost and accelerate the process of innovation in India, you can do that using modeling and simulation. Okay. So with that, I will now that I've made a case that yes, modeling and simulation is needed in this particular industry, let me jump to what I mean by modeling and simulation. So what you see on the left hand side is a real coupon, real 3D printed multi-layer thin wall. What you see on the second image is a high fidelity melt pool dynamic simulation. It's a multi-physics particle dynamics coupled with laser dynamics coupled simulation of a thin plate. Then you have a microstructure growth simulation where you can see thin, long columnar structures not desirable. And the last one is FEA based. So the first one is experiment, second one is CFD, third one is Monte Carlo, and the fourth one is FEA based stress and deformation simulations. Okay. Um, there are multiple processes in additive manufacturing industry. LPBF, which is laser powder bed fusion, WLAM, which is wire laser direct energy deposition, wire arc additive manufacturing. So first one is based on powder and laser, second one is based on wire and laser, and third one is based on electromagnetic forces and wire. Okay. So we are here. A lot of you come from the CFD background, so you might be curious to know what are the equations that are being solved in really, simulating these complex processes. So of course, we need our glorious Navier-Stokes equation. There could be some additional force terms. For example, in the case of electromagnetic forces, we have added additional force terms to the original momentum equation. Uh, one critical and the probably the most important piece of physics here is the multi-phase interface tracking. So we are using four-phase multi-phase system. Why we need four phases? So the solid metal, the molten metal, the vapor metal, because temperatures can easily exceed 3000 and 4000 Kelvin in these processes. And the last one is the ambient gas or the inert gas in which the entire 3D printer operates, or the chamber of the 3D printer operates, right? So we have four phases, and at all times we are tracking the interface between any of the two phases. We need temperature dependent properties. This is another critical piece because you're going all the way from 300 Kelvin to 5600 Kelvin. So your properties significantly change as the temperature changes. Surface tension forces, Marangoni convection, which is basically temperature dependent surface tension that causes your molten metal to accumulate one part of the domain and leave certain other parts of the domain. Okay, so that is on the CFD side. On the DEM side, we are using a lot of particle modeling where we create the powder beds. Uh, and then there's a lot of defects that we were talking about. We were talking about keyholes. If you notice this particular animation, this is my favorite one. You can see a laser being shot at a metal, and just notice the fidelity and the capturing of a huge air bubble inside this melt pool, and some spattering is also visible. Okay, so the air bubble will be entrapped. Yes, there it is. Okay. Then these days, people are trying to work with new shapes of lasers, which is, I believe we do not have any laser beam shaping facilities in India. But that doesn't mean we can do research on that. In fact, researchers from a few IITs are already working on this, and they're very interested in understanding the impact of, for example, a ring shaped laser beam on the microstructure of the metal. And for that purposes, simulations can be used because you actually don't have a ring shaped laser beam. Okay. Then you want to understand the thermal cycling plots based on the fluid thermal interaction. You want to understand spattering and such things. Okay. So that was all CFD. Now moving on to the next part, which is the microstructure evolution, because we don't want to solve just CFD, and because that is not really the complete story when it comes to additive manufacturing. We are talking about Monte Carlo methods. We are talking about crystallographic plots, and the main focus here is this is the type of data that you would get from tomography, tomography experiments that I mentioned earlier. But what you have here is actually coming out from simulations, very detailed slice by slice, time dependent microstructure evolution at different parts in your metal block, as the laser melts and solidifies it. And what you have on the bottom right is one of the relatively new developments at Pandav, where we take the entire CFD melt pool dynamics data, and we try to capture the exact melt pool from CFD, and we simulate microstructures inside that melt pool only. Rather than assuming a perfect hemispherical shape of a melt pool, we actually take the real melt pool shape and the temperature history from the CFD data. Okay. So how does it look in coupling with each other? Melt pool dynamics, which is CFD, when coupled with microstructure, which is Monte Carlo. So you see on the left hand side, the blue color on top is the vapor, and you can see how the melt pool is dynamically changing as it solidifies. You can see the microstructure evolution as well. You can even see a single, spot of yeah, some of the vapor is also entrapped here. How does it look in comparison to the experiments? I mean, it's quite well actually, compares quite well. So if you see some of the part of the vapor was probably entrapped here, either that or the experiment failed to measure the microstructure data here. It is one of those things. Either way, This is what we are simulating from simulations, and you can see very nice microstructure data. You can even see a bubble entrapped here, and then in the previous simulation you can observe one of the bubbles which is formed here it is, and then it flows to the bottom top. Okay. So the end-to-end simulation for additive manufacturing, powder to part scale is our goal, and cutting down the cost by 67% in the initial process optimization phase itself. Now, some of you may wonder, you are really not, covering the entire pipeline, because the additive manufacturing doesn't start where you already have powder, you already have some metal with you. It actually starts at the powder manufacturing state itself. In fact, for that, we are already working on gas atomizers, supersonic gas atomizers, where powder is actually manufactured with accurate sphericity being captured. We take that powder, prepare powder bed using discrete element method or particle dynamics. We take that data, shoot laser at it using CFD plus Lagrangian laser dynamics approach. We take that data, put it into microstructure to capture the grain morphology, grain microstructure, take that data and put it into part scale FEM. Okay. We'll look at the three case studies here. Different sorts of laser uh, parameters and we'll see how the results change. In the first case, we are looking at pure aluminium laser being shot at it. In the second case, we are looking at ALSI 10 mg, heavily used in defense these days. We look at the LPBF process for that. And in the third case, we will look at a multi-material, which is aluminium and copper multi-material building or welding, if you want to call it. Okay, so let's start with the pure aluminium 3D printing. Left side we have the experimental video, right hand side we have the simulation video, and you can, if you observe carefully, you can appreciate the fidelity at which not just the vapor is captured, but each and every pore is captured as well. Okay. In this case, people are very interested in understanding what is the front angle of the melt pool, because that apparently decides the microstructure as well. So in the experiments, they were getting around 85 degree as the front wall of the melt pool, and we were getting around 85, 82, 81 when taken at different sections. Once again, this is the top view. Okay. And right hand side is experiment, left hand side is simulation. A lot of pores uh, are entrapped and left behind permanently in the part, which is quite bad. Okay, second case is ALSI 10 mg, where we are looking at uh, depth and width of the melt pool, and we are getting, in width we are getting deviation of 5 to 20%, in depth from 3 to in some cases up to 40% depth variation is also there. Now this material is very is heavily under research right now because of its high printability, balanced mechanical and thermal properties. It is lightweight. It is easy to post process, compatible with post processing, and already has a good track record in aerospace and defense, or about to have a good utility. Thermal and corrosion resistant, it can be tailored for microstructure, desired microstructural properties as well. So some of the defects that were not visible earlier could be seen here. You have some pores, you have a depression here, some defects at the end of the build, and this is not desirable. Some of the structural defects that we can see here in terms of microstructures, and again we are comparing the simulation data with experimental data. The trends match well, except for a few exceptions, and of course this can be improvised even further. The third one is quite interesting: aluminium and copper multi-material welding, where used in battery systems. It is used in electric vehicles and aerospace, where aluminium carbon fiber composites are made. Biomedical, where metal and ceramic interfaces are made, and in additive manufacturing for sure. Okay. So just look at the fusion zone. On top you have aluminium, bottom you have copper, and you can see a nice fusion zone and a well create a sort of a dune formation as well. Okay. Moving on to the next scale, which is the part scale modeling. We have actively started working on closing the cycle of capturing many scales. So the largest being the part scale, where people are mostly interested in deformations, in thermal and thermomechanical stresses, and the orientation at which you build a certain part in 3D printing can give you very different results in terms of stress management, thermal stress management, in terms of distortion minimization. Okay. Okay, so how does this all connect to open source? FOSSEE is all about open source, and not even once have I mentioned that this is open source. Open source is free of cost, as Mrs. Payal mentioned earlier. But there's another huge advantage of using open source frameworks, which is for a country like India, which is still in its initial stages of development. This gives power in the hands of users, in the hands of students, professors, and researchers to take the fundamental equations and build and apply them to their particular needs. So in our case, we took a huge gamut of open source libraries, all the way from OpenFOAM, Lights, uh, many of the AI based TensorFlow, GPU based libraries, uh, and, and and other libraries as well. We took them all, and we found that at the end of the day, it's the same fundamental equations that are going inside ANSYS or AM Prava. But then what's stopping us from creating softwares like ANSYS in India? It's uh, our resistance or hesitation in using open source frameworks. So what we did, we took all these libraries. We realized that they are great libraries, but unfortunately they are also limited in some capacities in terms of what the industry application wants. We basically coded our own equations, we added our own codes, modified the libraries, corrected their bugs, added a user interface, parallelized the libraries, and we did entire process development of that a software should go through, and we created AM Prava out of it. So open source is not only good for just saving the cost and learning, it is actually good for accelerating the pace of innovation for any country. So I would urge all the students, especially, and many of the professors, to stay connected with FOSSEE. Contact us if you want at any time, and get your fundamentals straight. And the only way to learn good fundamentals of CFD is by learning open source. And OpenFOAM is one of those great pieces of software, or I wouldn't call it a software. It's a bunch of libraries to get started. Okay. So a little bit about Pandav applications. We are located in Bareilly, Uttar Pradesh. We provide computational engineering, simulation software development services across multiple industries. Today, I talked only about additive manufacturing, but we do a lot of work for data centers, for mining, metallurgy, um, food industries, automotive, aerospace, defense, and you name it. I mean, basically, truly industry agnostic. Okay, so thank you very much again for having me, and I will be happy to take any questions.
So there's one question in the chat by Mr. Arvind. He's asking, I have a question to Professor Advait. You mentioned by experimenting via simulation also have its cons, considering the minimal cost expenditure when compared to experimenting via XCM or XRD, etc. Could you elaborate on it?
You mentioned by experimenting via simulation also have its cons, considering them. Yes, I mean simulations. It's a cost on electricity, it's a cost on computers, it's a cost on manpower. So even if you go ahead with a completely free simulation software, I mean there's always a cost associated with everything, but that cost is significantly lower when compared to the experimental cost, because if an experiment such as synchrotron and an XRT experiment goes wrong, there's a huge cost associated with it. But when a simulation goes wrong, you can just crash your simulation and restart it. However, I mean, I'm just saying that the costs are significantly different for the two. Material properties are very important in these types of simulations. How to get accurate set of. Yeah, so this is a great question, and material properties are around 10 to 15 material properties we have accurately captured, not by experimentation, we'll be very honest, but by a lot of good work done by research labs all over the world, and as reported in the research papers as well. Uh, but when it comes to new alloy properties or super alloy properties, this is something that needs to be gathered in a careful manner. We don't work on that side of things, so I have limited comments on that. So far, 99% of the alloys that people are considering are already being modeled and simulated. Follow-up question, but how are the performance and output compared to experimental? Like I said, I mean, it depends. The more accurate you set up the simulation, the more accurately you provide the material properties, you can get into the realm of 90 plus percent accuracy with simulations compared to experiments. But if you want to run on coarser meshes, if you want to make more approximations, then your accuracy starts dropping and it can go down up to 70-60% as well. High temperature responsiveness for also, what do you think is the biggest challenge for industry absorption for AM, obviously, other than high cost of R&D? Well, I mean, AM parts inherently go through a huge temperature range. You start with a preheated 500 Kelvin plate, and then your powder is basically, 350 Kelvin powder, and then you start heating them, take it up all the way up to 5,000, 6,000 Kelvin in some cases, cool it back down. So your basically your metal has seen a huge and aggressive temperature changes already. So later, when it is thrown at real operational conditions where your temperatures are changing very fast, in those cases AM parts are likely to be more robust in their operation. What is the biggest challenge for AM? I feel the biggest challenge is the slowness in terms of the research, in terms of completely understanding the materials and their response to the process parameters as well. Could you also please computational? Yes. So computational time, as we all come from this domain, we know the same simulation can take 15 minutes and it can also take 15 days. And that is the case with most of the simulations in this presentation. Most of them are a few hours long simulations, but then we have run simulations that have run through for 7 days to 14 days. The very similar simulations. So depends on what you want. You're fine with 70% accuracy. That's okay. If you want to go up to defense sort of activities, then maybe even 95% is not enough. If accurate material property, what is the other way for consideration? If material properties are not available, then you have started approximating already. And up to my best knowledge, you can use some empirical approaches in estimating those material properties. CalFat gives you some of them, but then at the end of the day, if you don't know material properties well, you will see the effects of that in the overall accuracy of the simulation. Can we use open for combustion simulations? I Yeah, I mean, you can. I think other people will also comment on that. How are the CFD results validated in the cases here? Oh, they are validated with the real experimental data collected from the research labs, from our actual users. So we have around 10 research users all over the world right now, and they are, you know, trying to validate our results. Reason behind after CFD analysis also failure of components. Well, because it's very new. In if you were in or aerospace industry, you wouldn't say this because there's a huge trust on CFD simulations. But when it comes to additive manufacturing, it's a relatively newer industry, and hence there is not much. So start with, there's not much CFD analysis happening in additive manufacturing industry. When sufficient analysis starts happening, I think the scenario will change. How DEM, CFD, and microstructure in terms of we do not couple them at the equation level. We couple them in terms of data transfer. We take data from DEM, put it on CFD. We take data from CFD, put it on micro level. Because if we couple everything and make a huge matrix which is out of control, it will become a good research project but never be useful for the actual user. Any further questions?
I wanted to raise a few, and maybe your experience will help the audience in that case. So basically, as you know, the vision of this workshop is just, we have so many new users of OpenFOAM or students, particularly who would want to get motivated to cross the steep learning curve of OpenFOAM, and that's where we want to basically show them what is a real life application of OpenFOAM. As you said, it's not only for research project, just for writing papers, but also for actual real life applications, and it can really reduce the cost of these commercial licenses and help SMEs, smaller businesses, to come forward and do their business. So and I think we had this discussion personally before, but I want to make it in a public forum just again. So while building this startup based on the open source tools and modifying them and everything, but when you actually present them to um, your clients or whoever wants to take this tool and use in real life application, what do you feel about the challenge in the mindset in terms of uh, skilling up the workforce and training the workforce in the industrial scale?
One challenge that we face is people asking us, because they are already using ANSYS or some other software, so they will have to learn a new piece of software, and that is a fair question, I would say. But that's the nature of it. If we can show them that, look, this is a new software which not only uh, exceeds the capabilities in certain areas. I wouldn't say we compete with ANSYS or anything, but in certain areas we are better. If you can show that, and if you can also spend time from your side in scaling up their workforce, I think they're very open to adopting any software for that matter. Also, it depends on the country. When we pitch this software to American audience, and we tell them that, look, the engine in the background is a bunch of open source libraries, they get very excited about it
Yeah.
because they have heard the names, they have probably used it in their academics. The situation is different when it comes to India and similar countries, where when we say that the backend engines are actually open source libraries, then there's some resistance there. But I think it's changing with time. 5 years ago, it was almost impossible to convince anyone that anything can be done in open form in real world. But today they are paying us to do that. So I think things are changing very fast now.
Yeah, I mean, towards that was exactly my next following question, that what is your verification and validation strategy from your company to convince your clients that, yeah, OpenFOAM can do, not only can do real life simulations, but also can do with the same level of same order of accuracy as the commercial codes? Because there are some myths that if if the users pay for the licenses, the simulations are more accurate. And this is not only in India, it is worldwide. So how do you overcome that, and what's your particular strategy for verification and validation?
Right. Verification is something that can be done from our internal coding point of view, but validation is something that is more inclusive, And we do collaborate with universities, with research labs. We ask them, you give us our data, let us compare our simulation data with your experiments, and if it matches well, I think, I mean, even they build trust. And most of the customers, they do not just right away take our product. They of course want to make sure that at least for a few cases, the results are matching their experiments. So that is something that is some extra effort that we have to put from our side as of now.
Right. And I was actually very curious in terms of, like, you have partially answered that. So, for example, in aerospace industry, which I am mostly involved in, um, the real life applications or industries, they are very concerned about the turnaround time rather than accuracy. For example, of course, most of the aerospace industry uses URANs instead of LES or DNS, because we cannot really afford to do that in industry scale. Or in most of the scale, we also industries also depend on model order reduction, some reduced order models, just to get the back of the envelope calculation, which with some factor of safety would suffice for their design and will always be on the safer side. So we really don't want to know that minute underlying physics for industry purpose. So I was basically more or less curious on additive manufacturing side, what's the mindset in the industry? Would they really want to go for that scale resolving simulation, or they are happy with coarse mass, I mean, more or less accurate simulation where the results are within the same ballpark? Or do you have also provisions for model order reduction? Do you think these high fidelity simulations can lead to some reduced order models, which can be better used in the industry scale?
Right, it's a mix of both actually. People who are into pure research, I mean, uh, they of course want high fidelity simulations, but industry users, where the turnaround times, like you mentioned, have to be very quick. They don't care what we are using in the backend; they just care about the results. So for that matter, we have started developing. I wouldn't say low order. I would say low dimension models, instead of 3D, some approximations onto 2D, and then some all the way up to 1D. In fact, we have developed something for a company. It's an electron beam 3D printing company based in Europe. And I mean, we are currently doing 2,400 layers of simulations under 20 minutes, which, if you do with CFD, it will take years. So, of course, if there is a requirement, then we care about solving the problem and not just forcing high fidelity simulations down their throat. That's not our goal. But it's a mix of both. There are people who are not happy with these equations. They say, there's just something missing here, something, you add this. So we are open to everything. Whatever their requirement is, we develop accordingly.
All right. I think for the sake of time, we can keep discussing and I will lose track of time. So I'll just hand over this to Ismail and Ivan and whoever are coordinating this. Thanks, Advait. So I wanted to just thank you on behalf of the FOSSEE team for your time and sharing your knowledge and your real life experience of building the startup. And I think it's contributing significantly in the additive manufacturing side in the India, and I keep following. So thank you very much. And we really appreciate your experience sharing with all the particularly new engineers who would like to use OpenFOAM and for real life applications. Thank you very much.
Thank you, Dr. Bose, and it's nice to see you again. These are
Sure.
the platforms that gives us the opportunity to meet again.
Sure. All right. Thank you.
Yeah,
Yeah,
thank you
Ivan,
so much,
over.
Mr. Advait. So I think this session was really very, very helpful for the students who are now, studying and colleges, and they're aspiring to join the CFD industry because they got a very deep insight about whatever Mr. Advait is working on now. And yeah, thanks a lot. Thanks a lot for joining.